Right, in today's lesson, we're going to look at function transformations, and ultimately we're going to learn how to graph piecewise functions. Most functions will take the form y equals plus or minus some value a times f of plus or minus b x plus or minus c plus or minus d. Okay, so this of course looks very complicated, but most of these we're pretty familiar with. If you have a function and there's some plus or minus towards the end, we should remember that this is some vertical shift, up or down. Up, of course, being the positive, down being negative. Okay, so if you see like a quadratic and there's a plus 5 at the end, we know that at some point this thing's getting moved up 5. Okay. Similarly, there's this plus or minus c here inside the parentheses, so kind of being evaluated in the interior of the function. And this is a horizontal shift. Horizontal shift. And this would be left or right, of course, where left is positive and right is negative. You may remember from Algebra 2 and Pre-Cal that when it's inside the parentheses, everything's kind of backwards. There's this value b, which is a horizontal compression by a factor of 1 over b. So instead of, like if this was a 2, you would divide the x values by 2 instead of multiplying. I don't know that we're going to see a whole lot of this until we get to trigonometry, so I'm not going to worry about defining this value b, but it is possible that many functions have this, but we're not going to encounter them just for ease. Although it could be the case that inside the parentheses, the number in front of x is positive or negative. If it were negative, that would be a reflection over the y-axis. Okay, so in all of our examples, the value b is going to be equal to 1, so it'll look like 1x or just x. But this could be negative x or positive x, and if there's a negative in front, that's a reflection over the y-axis. There's the value a in front, which is a vertical shift by a factor of a. So if there's a 2 in front of your function, you're going to take your y values and multiply them by 2. If there's a 15, you're going to take your y values and multiply them by 15. If there's a 1/2, you're going to take your y values and multiply them by 1/2, or divide by 2. Okay? So this is a vertical stretch by a factor of a. And then finally, if that value in front of a is negative, that's a reflection over the x-axis. Okay? And these are all the possibilities that we can encounter when we talk about transformations. Hopefully this is all a big review, but just as far as order is concerned, we always want to go left and right first. So that's that value c there. If you see like an x plus 5 or an x minus 6, we always want to take our original function, our parent function, and move it left and right first. The last thing we want to do is go up or down. That's that value d there at the end. And honestly, that's the only rule we need. As long as we're going left and right first and up and down last, it's not going to affect anything. But in case you want a kind of an order, here's how I like to do things. I'll go left and right first. Then I will handle any reflections. So reflect over the x-axis or the y-axis. Remember, a reflection over the x-axis is the negative on the outside. A reflection over the y-axis is the negative on the inside. So do one of those. It's not going to matter which way you reflect first, but do one then the other. And then the final thing would be the vertical stretch. That's that value a. And then go up or down. So if you're starting, going left and right, if the second thing you're doing is handling any reflections, the third thing you're doing is taking your y values and multiplying them by a, vertical stretch by a factor of a, and then the fourth thing you're doing is going up and down, you should be in good shape. For those of you who are curious, if there is a value b here, you could handle it in this step. But like I said, for all of our examples, we'll do b equals 1, so it's not going to matter. All right, so here let's just list what are the transformations here. Well, the first thing we should probably do is identify the parent function. And it looks to me like there's something squared. So the parent function is y equals x squared. And I'm not going to spend a lot of time, or really any time after this in this video, talking about parent functions. We should know that the quadratic parent function looks something like that. Okay, but clearly this function and the parent function are very different. Something has happened to our parent function in this example, so how has it moved, right? Originally it looked like this, but then somehow this function has transformed it. So in order, what's happening? Well, I always start with left and right, and I see there's an x plus 4. So the first thing I see is this thing got moved left 4. Okay, then what? Well, there's no reflection over the y-axis, but there is a reflection over the x-axis. There's a 3 out front, so it's a vertical stretch by a factor of 3. I would multiply by my y values by 3. And then the last thing is this up 5. And those are the 4 transformations that have been taken to go from the original parent function to this function. Let's do a couple more here. Let's look here. First, the parent function is y equals x squared. So maybe just over here. That's my parent function. That's what this thing looked like originally, but then now it's been moved. It looks like to the right 2 and a vertical stretch by a factor of 2. Those are the only 2 transformations here. In example 2, the parent function is the absolute value of x. So you may remember that that looks like this v here. Okay, but then this one's been moved left 4, reflection over the x-axis because it's on the outside, and then I want to make sure the last thing I do is this down 7. Cool. And so it wouldn't be very difficult. We're not going to do it explicitly, but I can imagine moving this whole thing left 4, reflecting it over the x-axis. So if I move it left 4, it might look like that. If I reflect that whole thing over the x-axis, it might look like that. And then if I go down 7, we might have a final graph that looks something like this. Okay? So it wouldn't be very difficult. If you know what it looked like originally, and you can describe how it's moved, graphing the function isn't too bad. Last one here. Looks like we've got a right 3, a reflection over the y-axis, and a vertical stretch by a factor of 1/3. Awesome. Okay, so let's practice actually graphing these things now. Forgive the fact that example number 8 got kicked here, so this should be y equals 1/2 the square root of x plus 2 minus 1. So for some reason when I printed it, it got moved down here. But in this example, we're just looking at this function, x plus 5 squared minus 3. So I'll do example 6 and example 8, and I'll let you try 7 on your own. There's also a key posted here as well. So if we just look at example 6 here, this is our standard quadratic. So I know for a fact that this used to be the function y equals x squared. I know that by the square here. So, and we won't do this in every example, but if you want to look at what it looked like originally, we know that the standard quadratic goes through, at least originally would have gone through those points. Hopefully you're familiar with why the function y equals x squared goes through those points. It looks like this. But this function is not what we're asked to graph. We're asked to graph x plus 5 squared minus 3. So it's now our job to identify the transformations in order. But this one's not too bad. It looks like left 5 and then down 3. So actually a pretty easy list of transformations. So because we know what it looked like originally, and we know how it's been moved, graphing it shouldn't be too bad. I'm just going to take each of these points that I know are on the graph of the original and move them according to my transformation. So left 5, 1, 2, 3, 4, 5, down 3, 1, 2, 3. Okay, do that for a couple more points. If I go left 5, starting here, 1, 2, 3, 4, 5, down 3, 1, 2, 3. I could do that for this point, and I would get here. I could do that for this point and get here and here, and we would have this function. So this function here in red is this graph. Okay? Hopefully not too bad. Let's look at example 8. Again, maybe it's helpful for some of you. Oh, they asked to state the domain and range. So the domain of this function is all real numbers. It is infinitely wide. If you look at just the x values, it goes left and right forever. The range of the function, so that's top to bottom, so the lowest point to the highest point. Well, the lowest point is down here at a y value of -3, and the highest point, well, there is no highest point. It just goes up forever. Okay, cool. I'll let you look at the domain and range for example 7, and we'll do example 8 together. So the first thing I'm going to do is identify the original function, which is the square root function. I know some points that the square root function goes through. And so I'm going to imagine maybe this graph. This is what the function would have looked like originally. So then how has it been moved? If I look at my transformations, there's definitely a left 2. There's definitely a vertical stretch by a factor of 1/2. If you call that a vertical compression, VC 1/2, that's okay. And then down 1. So just 3 transformations. So let's look at them. We'll go left 2, and then there's this issue of vertical stretch 1/2. All that means is take the current y value, multiply it by that number, in this case 1/2, and then plot that point. So let's look. If I go left 2, then I'm here. The current y value of that point is 0. And 0 times 1/2 is still 0. But then I move the whole thing down 1 to satisfy the last transformation. And I get this point here. Okay. Let's look at this one. Left 2. So that would put me... Maybe I do it in blue just so it's easy to see. That would currently put me here. Left 2. Okay, so that's good. Now I have to vertically stretch by a factor of 1/2. So I'm going to take the y value at this point. What's the y value here? The y value at this point is 1. This is at a height of 1. So I'm going to multiply that by 1/2. 1 times 1/2 is 1/2, and then down 1, that would put it right there at -1/2. Okay, last one. If I go left 2, puts me here. That's at a currently at a y value of 2. So if I multiply that y value by 1/2, 2 times 1/2 is 1. So that would move it down to a y value of now only 1. And then I would go down 1. This should cross the x-axis at 2. And then, now that I've transformed to those 3 points, I would have this graph here in red. Yeah, let's go ahead and do example 7 just so that we have it done, and then we'll end the video and finish the rest in the next video. So I'm going to go pretty fast here. I'm going to plot the parent function, y equals x squared. The domain of this function is from -2 to infinity. So just left and right. The furthest left it goes is -2. The furthest right it goes is infinity. The range is the lowest that this graph goes is -1. And eventually it will rise to infinity. It doesn't look like it because it's going very flat, but eventually this thing will rise up forever. Okay, so example 7, I'm plotting the parent function, which is y equals x squared. Okay. So that would look something like this. I'm going to apply the transformations, which hopefully you all agree are right 2. Reflection over the x-axis, vertical stretch by a factor of 3, and up 4. So quite a lot going on here, but let's see if we can't take it one step at a time. I'll go right 2. So for every point, I'm going to go right 2, multiply, right 2, reflect over the x-axis, multiply the y values by 3, and then go up 4. So right 2 puts me here. If I reflect a point that's already on the x-axis over the x-axis, it doesn't go anywhere. The current y value at this point is 0, and 0 times 3 is still 0, so that's good. That doesn't move. And then finally up 4 would put me right here. Another point. If I go right, oh, dang it, I went left. So I should have gone right 2, reflected over the x-axis. So that would actually be here. So this is wrong. I should have gone right 2, not left 2 like I did. This point. If I go right 2, it's here. Reflect over the x-axis would put it here. Vertical stretch by a factor of 3. My current y value is -1. -1 times 3 is -3. And then up 4. 1, 2, 3, 4. And due to the symmetry of the quadratic, we can kind of extend. It would look something like this. Last thing for this video is going to be this problem here. We're asked to identify the transformations of the graph and write the equation. So this is definitely as a parent function, y equals x squared. But what would have had to have happened to the function y equals x squared, which we know originally would have looked like this. So clearly it got moved 1, 2, 3, 4 spaces to the left. It also got reflected over the x-axis and then finally got shifted down 1, 2. I hope you agree with that. If I took this curve here, moved it to the left 4 units, reflected it over the x-axis, and then moved everything down 2 units, we would have arrived at the exact point that we're at. So what is that as a function? Well, let's do the left 4. That's definitely an x plus 4 inside the parentheses. Don't forget the actual component that makes it the parent function, the squared. There's the down 2, which that's pretty easy to write. And then this reflection of the x-axis, that's just a negative sign out front. So then there's our function. This blue curve here has a formula, negative x plus 4 squared minus 2.